All right. Yeah, I don't know. Stefan, do you know the name of the person who created this Discord server?
No.
Yeah, I don't know who it is, but they have some really good problems. So H is the orthocenter. And we want to see where BO meets CH and, okay. So BO meets CH and CO meets BH. So we'll get a couple points here. This feels like the isogonal line lemma, but we'll see. Yeah, because like these are isogonal, these are isogonal. BO meets CH at Q and CO meets BH at P. And OH meets BC at R. Interesting. So you have a little quadrilateral there, and this is R. And then we have the circumcenter of APQ. So this circle here, we want to show that A, S, and R are linear. This is interesting. All right, so I'm going to draw the feet of the altitudes and then hide a bunch of stuff. Okay, so that's OH. BO and CO. So these are isogonal, these are isogonal. So we have isogonal conjugates, right? So P and Q are isogonal conjugates. So, and maybe I should draw the pedal circle because, you know, like this is perpendicular. It might help to draw the pedal circle of P and Q. Should be this circle right here. I wanted to intersect BC, but it's not easy to make it do that. Yeah, you got to make it like a tall triangle if you wanted to intersect BC, something like that. Actually, I think it always intersects BC, that circle. Yeah. It's just, it looks nicer if these aren't so close together.
Can you intersect PQ with BC?
Yes.
Then we have harmonic points.
So what points are harmonic?
BC are G.
Yeah, because these concur. So yeah, we have two pairs of isogonal conjugates. P and Q are isogonal conjugates, and O and H are also. And I think there might be some theorems that like exist for when you have two different isogonal conjugates, but I don't know them that well. I was thinking this might be an easy one, but this looks kind of hard too. Let's see if we can use the isogonal line. So I wonder if AR is isogonal with something. So like, can we use the isogonal line limit somehow? Like, because we have AB, AH, AO, AC are isogonal. Can we say like, can we intersect like OH and BC is R, and then OC and BH is P? I don't know if P and R are somehow like isogonal some way. Let's see. So yeah, okay, we have AB, AH, AO, AC, right? The isogonal line lemma says we can let those intersect. We have point P. And then, oh, but we already know P and Q are isogonal. We have this also. Yeah, whoever, I don't know who this guy is that has this Discord channel, but these are some really nice problems. I could probably spend a while trying to solve this. So, I mean, I guess we want to show angle SAQ is equal to angle RAQ. That seems like one way to do it. Why Q and not P? Yeah, we'd want to break the symmetry somehow. Yeah, it's just this fact that you're letting OH intersect BC. I don't know if there's anything special about that point in general. That's like the Euler line. So we know the center of this circle is the midpoint of PQ. Maybe that'll help. So yeah, I is the center of this circle. And then is I anything special? And the midpoint of OH is the 9-point center, of course. So actually, if we take the midpoint of BC, if we use the Gauss line, IJ passes through the 9-point center, right? I just don't know how useful this stuff is, but it's interesting. And yeah, that's kind of obvious because we know BDC is cyclic. And we know the 9-point circle passes through D and E. So those three centers should be collinear. I wonder if I just came out with another proof of the Gauss line. I don't know. Actually, I think I might have. No, I don't think that proves the Gauss line. I'm just going to delete these for now. Is there anything else special about point S? Don't even, yeah, I'm just totally guessing stuff here. Maybe there's something special about this line. Let's see. No, those don't. I thought those can curve for a sec, but no. Anything special about this point? I'm just totally guessing here. Do we have any orthocenters? So yeah, I feel like you need some sort of lemma on isogonal conjugates here. I feel like there's probably something. Yeah, I feel like there's some lemma on like isogonal conjugates and orthocenters. So like you said, RBG and C are in harmonic conjugation, right? So we want to show that AS, AB, AG, and AC are in harmonic conjugation. I'm guessing that was kind of your idea, right? And so maybe we could try to project through A onto some other line, maybe DE, or let's see. So if we draw AG, maybe we could project those 4 points onto DE and then show that those are harmonic? That actually seems like the best idea we've had. Yeah. So we'd want to take that intersection point and show that those are harmonic. Is there another way to do this? What about instead of DE? What about maybe SG or something? Or
maybe we project onto the circumcircle of APQ. Because one thing we know is that if we take the two intersection points with AB and AC, then this is parallel to PQ.
IJ is parallel to PQ?
Yeah, because P and Q are isosceles conjugates. And
okay,
then the angle there by A is the same.
that makes sense. So if we project onto the circle, then we'd want to draw a R, and we want to show that this is a harmonic quadrilateral. So we can hide S for now. We want to show that KJ, KJ, this point in I is a harmonic quadrilateral, KJLI. Okay. And we know that, like you said, JI, sorry, PQ is parallel to JI. So then we could try to project. Yeah, I like that idea. Yeah, point L is kind of tricky though. The other option is to project onto the circumcircle of ABC, right? Because then we'd already have B and C. And then we'd have this point. And this point. So then we'd want to show ABCN is harmonic. Let me just check that that's true. So that would mean the tangents at M and N would concur on BC. And they do. So MBNC, we want to show that's harmonic. And G, the trick is point G. So, well, what we could do, what if we take MBNG and we project through point G? So B and C just get swapped. N goes to A and M. Okay, so this is interesting. M would go to point. So we want to show AT as a symmedian. That's interesting. So we don't even really need point N. Yeah, we just want to show AT as a symmedian. Let me check that that's actually true. Oops. BAT and UAC. Yeah, I like that. Doesn't that look a lot easier? Like, so yeah, you let OH intersect BC at R, you let AR intersect the circle at M, and you let, yeah, you'd still need point G though. You have to let MG intersect at T, and you need to show AT as a symmedian. Yeah, maybe that's not easy. Or we could let AT be a symmedian, and then we want to show, yeah, there's a bunch of different ways of doing it. Yeah, we could let AT, we could define AT to be a symmedian, and then we want to show that MT, BC, and A. How did I define this? We want to show MT, PQ, yeah, and BC concur. You guys want to see if we can find an easy problem and solve it? Or we could stick with this, but
pardon me, could you repeat it?
Oh, you guys want to see if we can solve like at least another easier problem? So move on and then come back, or do you want to keep working on this? It's up to you all. If you want to keep working on this, that's fine.
I think we can go to the next one. I don't really like this problem.
Okay, it just looks really hard. There's a problem that Simon and I worked on, and we got really close, but we didn't end up solving it. So maybe you guys, this one looked interesting. So yeah, I don't think yeah, let's see if we can solve it. So, and I can tell you the ideas that we had when we worked on it last time. So, so E and F are actually any points on AC and AB. So it's kind of a very flexible problem. So BE meets CF at J. And then the circle AEF meets ABC at D. BJ meets ABC at P. And AP meets BC at D. Oh, whoops, I already made it. So this I should, Q, I mean. We want to show that OQ. So O is the, yeah, I forgot to write what O is, but O, I think, should be the circumcenter of ABC. We want to show that OQ is perpendicular to EF. So yeah, it's interesting because yeah, E and F can be any points on those sides. Circumcenter. I'm just going to put this in the description of the problem. So yeah, if anyone's watching it on YouTube, they don't get confused. So yeah, Simon and I try to use Bricard's theorem a bunch of times. And we got kind of close, but I'll see what you guys think. One sec, I'll be right back. All right.
The problem should be equivalent to the fact that FE is parallel to the line you got when you intersect AB and PC.
Yeah, that's what Simon and I figured out last time. So I'll draw that in, but yeah. Okay, so you're thinking about it the same way that we thought about it. That's good. These and these, right?
Yes.
Yeah. So yeah, we want to show EF is parallel to GH. I'm kind of happy that we thought the same thing that you thought, but then also this is kind of where we got stuck. So we'll see. Stefan, did you see this one before?
No.
Okay.
We can probably try some inversion at A.
Inversion at A.
Yeah.
Okay.
That EF parallel to GH is like equivalent that circumcircles of AEF and AGH are tangent, and after inversion we would get another two parallel lines.
Okay. So do you want to invert about like an arbitrary radius?
Yeah, we can try.
Okay. So yeah, we want to show the circumcircles of those are tangent. So yeah, we could just try like inverting about this. So yeah, so like this circle would invert to that. Let me just, yeah, we want to show the circles invert to parallel lines. So what do you get when you like, do you have an idea of like how to use like anything else with that inversion?
Yeah, I have no idea if it is actually useful.
Okay. Oh yeah, and then I think we try to use Pappus too. So FH, we know FH and GE concur on PJ. Yeah, of course, DFE is similar to DBC. Yeah, we have to use something about the point B. So yeah, I mean, it's kind of equivalent to showing FIE is similar to HIG. So maybe we could try to see, like, we want to show a homothety at I takes triangle IFE to IGH, but maybe we could try to see where it takes D. I don't know if that would help. Well, then we would have like a parallelogram. Yeah, so what if we try this? I'm going to shrink the diagram a whole bunch because I want to, basically I want to draw a parallelogram GAH and another point. And I don't know if this is going to work, but I wonder if okay, so takes IFE to IGH, and then we would have like, I guess it would take the circle of AFE to this circle. So is P? Okay, so it looks like it's probably by an angle chase we could show that, yeah, P lies on that circle. And also that homothety would like map D to this point. Yeah, I don't know if this is really that helpful actually, but sorry. And yeah, are these concurrent? I think it's not hard to show that those concur. Yeah. Let me make sure though. Yeah. So these are concurrent. Yeah, how is P defined again? That's where DJ meets the circle. Okay. So really we draw the circumcircle GPH. And then we let it intersect at a point M. And then we draw AM and we let it intersect the circle at K. Yeah, so we can do it that way. So we want to show that if we could show that KG is parallel to AH, that would solve it. So we have angle, we want to show KG is parallel to AH. So all right, Khan just joined. So let's see if he can help us with this. Hey, Khan, thanks for joining us. So we have a half hour left. I'm going to delete some of the stuff I added to this problem. But we have a problem. It looks simple, but it seems like it's kind of hard. So it's a very like general problem because E and F can be anywhere on side AC and AB, and then BE and CF intersect at a point J, and the circle AEF meets the circle ABC at point D. And then, yeah, I added in point I, but I'm going to delete it. So yeah, so we added in points G and H, but really the problem asks to show that OQ is perpendicular to EF. And we found that that's equivalent to showing EF is parallel to GH. So Khan, have you ever seen this forum before, the Geometry Discussions and Problems Discord channel?
No.
It has some really good problems. But yeah, I put the link in the chat. Yeah, I put the link in the chat earlier.
How many did we solve today?
We only solved one out of, so this is our fourth problem. We only solved one of them. But yeah, we got close on a couple, so we could go back to those if we solve this one. Yeah, it just looks like this problem is so general that there has to be, yeah, some trick. So yeah, we could try to show AF over AG is AE over AH. So I wonder, we know DFE is similar to DBC, but under that spiral similarity, where does A map to? How would I do that? Yeah, so I'll just hide O and Q because I feel like the more we can remove from this, the easier it gets. So yeah, does using Pappas actually help? I don't know. to go back to that idea where we use Pappus. So like we form a parallelogram here. Let's see. So is it obvious that I like, so I think it's easy to show, yeah, it's easy to show that GPHK is cyclic. But then is it also obvious that I lies on that? I think it is, yeah. It's easy to show that too. So we have that cyclic. So yeah, basically I drew a parallelogram here. I'm gonna hide this. And then basically I said by Pappus, we know that FH and BE, or FH and GE meet on that line. So there's like a point right there. We know F8, we know that meets on DP. We don't know that this line passes through it. So we know AI and K are collinear. We have to show that L lies on that. And then that would solve it.
This should be proven by just ratios, I think. That L lies on line AK.
Oh, really?
Yeah, yes, because we can use the parallel lines FE and GH.
We don't know FE and GH are parallel.
Oh no, yeah.
But yeah, it's interesting. So yeah, we know A, I, and K are collinear. Can we show that A, L, and I are collinear? But yeah, it seems like there has to be a solution that doesn't involve all this, but I don't know. Maybe we could use, so yeah, we want to show A, L, and I are collinear. Maybe I could try projecting. Like I was wondering, maybe I could show the cross ratio AD, AB, AL, AC is the same as AD, AB, AI, AC. So if I draw a L, and what if I let it intersect the circle AEF? Or maybe, like I'm thinking, what if I draw AD and I let it intersect GE? So yeah, I'm trying to turn this into a cross ratio problem. So at this point right here, so I'm kind of breaking the symmetry of the problem. But so I have AD, A, B, A, C, and AL. And I'm trying to project those onto GE. So that would be M, E, L, G. And I want to show that that cross ratio is equal to AD, AB, AI, AC. So yeah, what do I do with point L? That's the question. L. Wow, I can't believe these problems are so tricky. I don't know if point L makes things harder or easier, or if I should just get rid of it. But yeah, I don't know what else to do. Let's get rid of L. Yeah, what would be a way to bash this with AF over AG equals AE over AH? Can we just do a bunch of ratios and eventually get there? So yeah, how would we calculate AG and AH? We could try to use Menelaus, like GB over AG times AC over CH.
I think I solved the second problem.
Oh, really? Okay.
Yeah, the one with the angle bisector.
Okay.
Okay, so we don't need most of the stuff in the diagram. So the point I, yeah, that circle, point I.
Do you use point H?
Yeah, I use it. Yeah, we don't need K, we don't need L or T.
Okay.
Also point R. Just to make the diagram a bit easier to look at.
I know, I agree. But yeah, we still have E and F, right?
Okay, yeah. I will add in two new points.
Do you need this point?
No, I don't need N.
Okay. All right.
Okay. So drop a perpendicular from S to BC.
Okay.
Also intersect AD with EF.
Okay.
So the whole thing we want to show now is that EDF is 90 degrees.
Okay.
But also we can like angle trace that EUF is 90 degrees. So we want to show that EUDF is cyclic.
Okay.
And if we want to show that EUDF is cyclic, we want to use a powerful point. Or rather, we want to show that when you take the radical axis of AEF and SUD, and then H will lie on it. So basically, we intersect those two circles again, AEF and SUD.
Okay. AEF and what was the other one?
SUD.
SUD. Okay.
Because we have
right angles.
Yeah. Because of the right angles, we know that those two circles intersect on AD.
Okay.
So we basically, in order to prove that EDF is 90 degrees, we want to show that HS and AD are perpendicular.
Okay.
And we will actually prove that V is the orthocenter of ASH.
Okay.
In order to prove that. So that is actually not hard at all. Because we know that HBDC is harmonic.
Yes.
You can project through A onto EF, and you get that HFVE is harmonic. And J is the midpoint of EF. That is really important, because then we can use the well-known theorem about harmonics and midpoints, that JV times JH is JF times GE, but that is equal to JS times JA. And that proves that V is the orthocenter.
Okay. So
And
then
now,
that shows it's a right angle.
yeah,
Right
and
here.
now I think there was like another angle chase which would just finish it.
Okay, so let me start writing this out. Okay, so X, I think X we define exactly like we did before. And okay, so we need that these three concur, right? So we start out, let H be the intersection of EF and BC, right? And we need to know that HS is tangent to the circle, right?
Yeah, so I can guide you through my algebra approach to that.
I kind of remember what you did. So like you wanted to show that's the same as so H lies on the polar of O, so O lies on the polar of H, and so
It's actually not really important to show that HS is the tangent. It is rather more important to just to prove that we have a harmonic bundle.
Okay. So that HBDC is harmonic.
Yeah.
Okay. And that, so first we use Cheva to show that BE, CF, and AD concur, right?
Yeah.
Okay, so by symmetry, AF equals AE, so I'm going to start out right saying that. That's because S lies on the angle bisector. And then these triangles, we're going to show they're similar. So here's how I'll do it. So angle SBF plus angle SCE. That's equal to angle B minus angle SBC plus angle C minus angle SCB. And this is which is 180 minus angle A minus, oh yeah, I'm just going to switch around a few things. And then that's minus 180 minus angle BSC. And that is not hard to show, should be 90. So okay, I'll write out one more step. 180 minus angle A minus 180 minus so BSC is just 180 minus half of BPC. Or so yeah, I don't know if this is the fastest way to do that angle chase, but yeah, basically this proves that SFB is similar to SEC. And that means that BF over, that means that BF times CE is SF squared. And then once we know that, then we try to use Cheva.
I wrote the final angle trace in the chat.
Okay. So angle AFD equals angle ASC.
But that is after we prove everything else. This is
Okay.
just the finishing part of the problem.
So wait, so we try to use Cheva, right? And so that means that we want to show BF over CE is BD squared over CD squared, right? By the Samedian thing, right?
No, BF over CE is BD over DC, but that is BS over SC holding squared.
Okay, so
and then I use the Pythagorean theorem on BFS and CSE, and like you work a bit algebra, and then you get the equivalent thing of having those similar triangles.
So BF over CE, basically that would mean that's BS squared over SC squared. Right, I don't know if I wrote that right. BS squared over SC squared, which would be equal to BD over DC. And this is since SD is a Samedian in triangle SBC. And so by Cheva on triangle ABC, then we have AD, BE, and CF concur. And that means that we have a harmonic bundle. So BC, DH are in harmonic conjugation. Okay. And then once we have that, okay, so what do we do from there?
Project through A, and then we use that theorem about midpoints and harmonic bounds to get the orthocenter.
Okay, so we project those through A. And so this means that FE VH is harmonic. That means that JV times JH equals JF squared. Or I could say JF times JE. And okay, so once we know that, I forgot. How does that show that V is the orthocenter?
It is equal to JS times JA.
Okay, that's right. So this is equal to JS times JA. So this Yeah, this implies that V is the orthocenter of ASH. Okay. And then, so that implies that HS is perpendicular to AD. And so then we let HS intersect AD at a point. Do we need to do that? And then this is cyclic. So yeah, I could just draw on that point. It's gonna make it difficult for me. I'm gonna have to zoom in maybe. Or it won't let me do it. There we go. So let HS intersect AD at W. Let's move this all up. Okay. Let HS intersect AD at W. Then WSUD is cyclic. Whoops. Didn't mean to do that. What is going on here? Okay, there we go. All right. And then, so then what do we do from there?
You also need that AESWF is cyclic. Just write that and then powerful point you get.
Okay. Cyclic. And then by power of a point, actually we didn't even need this, but I will. So by power of a point, but we want to show EFDU is cyclic, right?
Yeah.
So HF times HE, I'll just say, so yeah, HF times HE is equal to HW times HS, which is HU times, was it V? HU times HD. So that means that EFUD is cyclic. And then once we have that, then we have angle EDF is equal to angle EUF, which you said was 90.
Maybe you don't need to write that.
Okay.
You can just like take the last angle trace.
Oh, what you put in the chat?
Yeah, I think now it is the time for it.
Okay. All right. It doesn't like the angle sign. It won't let me copy if I do the angle sign, so I'm going to have to type it out. Yeah, I don't know why it does that. Angle DFE, which is angle ASE plus angle EUC, which is angle ASE plus angle ESC, which is angle ASC. All right. Let's see. So AFD is ASC. And then that means those triangles are similar, which so triangle AFD is similar to triangle ASC, and that means that triangle AFS is similar to triangle, what is it? AFS is similar to
AFX is similar to ASC.
Oh, sorry, AFX. And that means that
you can basically from there you can get that EC, X, and S are concyclic.
Okay. So this means that, I mean, by spiral similarity, this means that CX is perpendicular to AX, right? Maybe you thought about it a different way. But so we want to show CX is perpendicular to AX, and then similarly BX is perpendicular to, or similarly BY, say AM, and then similarly BY is perpendicular to AM. So and that means that CX is parallel to BY. All right, so I'm going to add in one more thing because I don't think, hey, where'd that go? Didn't I just type it in? Did I like type it off screen or something? I hope this doesn't go off screen. What? Where? Oh, it's all the way down here. Okay. So yeah, it's off screen. All right. So yeah, I don't think we define point U. I'll just say define point U as shown. Or let U be the foot of the perpendicular from S to BC. All right, so thanks a lot for the solution. I'm glad we solved 2 problems this time. So yeah, we're a little bit over, so I'm going to stop here. But for everyone watching on YouTube, thanks for watching. And thank you all for participating. Yeah, I know it's a long time, but I really appreciate it. So if you want to join us in the future, feel free to email me at mgreenb801.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.